Welcome to Module 4, Part 5. In this part, we'll be discussing about the fabrication of N-channel enhancement mode device. Consider a simple fabrication process of a MOSFET transistor. The process begins with the creation of the gate terminal. Initially, the wafer is first oxidized. If you consider a wafer, a pure silicon wafer, where P impurities are doped in this pure silicon wafer to form the P-type material. The wafer is first oxidized in a high temperature of about 900 to 1200 degrees Celsius furnace that causes the silicon and oxygen to react and become a SiO2 layer. So over this SiO2 layer will be formed. So this is SiO2. Then an organic photoresist which is spun over this entire SiO2 layer. So this is the photoresist. An organic photoresist that softens where exposed to light is spun over this wafer. This photoresist is exposed through a mask that allows the light to pass through only where there should be some openings to be formed. Then the softened photoresist is removed to expose the oxide. Then the oxide is etched with a hydrofluoric acid where it is not protected by the photoresist. And then the remaining photoresist is stripped away using a mixture of acids called piranha H. Now a small opening is formed where the substrate is not covered with oxide. So over here let us draw then a silicon layer, and over this there is a photoresist. Then we have the mask which is open in between. So this is then it is exposed to UV light, ultraviolet light. So this is ultraviolet light. So when it is exposed to ultraviolet light, the area which is not exposed to light, so these are all exposed to light. So area is which is not exposed to light is soft, and this part can be etched off. So this is the P substrate, and the remaining photoresist can be removed. So when we do that, so only this area will be exposed. This is SiO2 and this is the P substrate. So now only this part is exposed. So now we need to form a gate terminal over here. Now how this is done? The transistor gate is formed next. So this consists of a polycrystalline silicon, generally called a polysilicon, over the entire thin layer of oxide. This thin oxide is grown in a furnace. Then the wafer is placed in a reactor with a silica gas and heated again to grow the polysilicon through the layer through a process called chemical vapor deposition. This polysilicon is heavily doped to form a reasonable good conductor. We will be forming a polysilicon. Over this we have the SiO2 layer. Then over this entire surface polysilicon is grown. This is polysilicon and this is SiO2. Then using a suitable mask, etching is being done to expose only the polysilicon mask. Next, over this an entire layer of photoresist is placed to form the source and the drain terminals. So Next, so this is the SiO2 layer. Over this we'll be having the polysilicon layer. So this is the polysilicon layer over which will be forming the gate terminal. So this is SiO2, then over this will be having the photoresist, next to form the source and the drain terminals. Then again masking is being done to etch off the suitable parts. So we have the silicon dioxide, then we have the polysilicon over here, then we have the photoresist on the entire surface. So this is the photoresist and this is the SiO2 layer. Then there is a mask. The top layer is exposed to ultraviolet rays, so then we have to expose this to UV rays. So the area which is exposed to UV rays will be hard and the remaining part will be soft. Then the remaining part will be soft. With this we can form a well-like structure right on the either sides. So the part which is soft is being etched off till the base material. We get a structure and the remaining photoresist is being removed. So we have the photoresist over here and this part is being exposed now over here to the left and to the right. A small part is being exposed. Here the silicon dioxide, this is the SiO2, here the silicon dioxide is patterned to define the wells. Now we need to add the N dopants to form the wells over which we have the source and the drain terminals. The well over here is formed by adding dopants and this is done by two ways, either by diffusion or ion implantation. In the diffusion process, the wafer is placed in a furnace with a gas containing the dopants. When heated, dopant atoms diffuse into the substrate. Second method is ion implantation. Dopant ions are accelerated through an electric field and blasted into the surface. Either of the method, the oxide layer prevents dopant atoms entering into the substrate where there is no well to be formed. So now over here wells are being formed either by diffusion method or ion implantation method. So over here we have the wells. So this is N plus well. This is N plus well and this is your P substrate. So now we have the well. Now finally aluminium is sputtered on the entire surface. Over here aluminium is sputtered on the entire surface and then it is etched off of the wafer, filling the contact cuts. Now the sputtering involves blasting the aluminium into the vapor that evenly coats the surface. Now the metal surface is patterned with a metal mask and plasma etched to remove the metal everywhere except where we need the contacts or the source and the drain terminals. So finally after etching of the metal, we will have a structure like this. And then we have the N plus region. Over here we have the N plus region. So this is the P substrate, and then we have the polysilicon over here, and then we have the metal, on the surface of the terminal to form the source, drain and gate terminal. So this is the gate terminal, and this is the source terminal, and this is the drain terminal. So this is SiO2 layer, and over here this is polysilicon, the polysilicon layer. So this is the polysilicon layer over here, and then the SiO2 layer, and then the source, drain and the gate terminals. Modern processes have around 5 to 10 layers of metals, so that the metals and the contact steps can be repeated for each layer. So this is the entire fabrication process of a N channel MOSFET. Thank you.